This lesson is on mole ratio. So mole ratio comes under the topic of reaction stoichiometry. Now, you sometimes hear that pronounced as reaction stoichiometry. But when I went to high school and at Villanova, we always said stoichiometry. So potato, potato, stoichiometry, stoichiometry, it's all the same thing. Okay, so what is it? Reaction stoichiometry is the mathematics of chemical reactions. We've done the mathematics of chemical compounds. Now we're going to do the mathematics of chemical reactions. To be able to do that, you must have a balanced chemical equation. So it starts with a balanced chemical equation. And we need to use mole ratio to be able to do that. Mole ratio is the moles of one substance compared with the moles of another substance. In a chemical equation. So let's look at a chemical equation and figure out the mole ratios. So here is our equation. We have 4NH3 plus 5O2 yields 4NO plus 6H2O. So let's talk about what these coefficients mean. So these are a counting number ratio. So this means that we have 4 molecules of NH3 that combine with 5 molecules of O2 to yield 4 molecules of NO, nitrogen monoxide, and 6 molecules of water. So that's our lowest whole number ratio. So if we had 8 molecules of ammonia, it would react with 10 molecules of oxygen to give us 8 molecules of NO and 12 molecules of H2O. 4 to 10 to 8 to 12 is a 4 to 5 to 4 to 6 ratio. We could have 4 dozen molecules of NH3. It would need 5 dozen molecules of O2 to react to produce 4 dozen NO molecules and 6 dozen H2O molecules. So a dozen, counting unit, 12, 4 times 12, reacts with 5 times 12 to produce 4 times 12 and 6 times 12. So of course in chemistry, we could have 4 moles of NH3, and that would need to have 5 moles of O2, and we would produce 4 moles of NO and 6 moles of H2O. So this just means we have 4 times 6.022 times 10 to the 23rd molecules, 5 times 6.022 times 10 to the 23rd molecules, etc., etc. So we maintain our ratio as indicated by the coefficients, 4 to 5 to 4 to 6. So we can take any two substances in our chemical equation, use the coefficients to write the mole ratio. So if we look at NH3 and 5O2, to write the mole ratio, we're going to do it as a conversion factor. We have 4 moles of NH3 for every 5 moles of O2. This is our mole ratio. And we could also flip that and say we have 5 moles of O2 for every 4 moles of NH3. Okay, so we could look at oxygen and water. In that case, our mole ratio is 5 moles of O2 for every 6 moles of H2O. And again, we could flip it and say we have 6 moles of H2O for every 5 moles of O2. So pick any two substances and use the coefficients in the balanced chemical equation. So now let's see how this works in terms of problem solving. So our question, how many moles of oxygen are needed to react with 2.78 moles of NH3? And remember, we always start out with our balanced chemical equation. So I've rewritten that. Then we go back to the problem, and I like to put my information underneath the substance in the balanced chemical equation so I can really see what two substances are being compared. All right, so how many moles of oxygen? So that's our X moles under the O2 are needed to react with 2.78 moles of NH3. All right, so that's right here, 2.78 moles. Now, I'm just going to do this problem using dimensional analysis. So start with your X moles of O2, set that equal to your quantity of interest, which is 2.78 moles of NH3. Multiplication sign and crossbar, just like all the dimensional analysis problems that we've been doing. For this, remember, you always want to have your substance formula. They're different on both sides of the equation. So we have moles of oxygen to moles of NH3. We're going to use our mole ratio from the coefficients. So our ratio is 5 moles of O2 to 4 moles of NH3. And we need to have the moles of O2 in the numerator. 5 moles of O2 for every 4 moles of NH3. Doing it this way, the moles of NH3 cancel out. The units on the right match the units on the left. So we're finished with conversion factors. Put in our unit of moles of O2. And now we do the math. So 2.78 times 5 divided by 4 equals, and let's see, 3 sig figs. This, the 5 to 4, the mole ratio, this is unlimited sig figs. It's exactly 5 moles of O2 reacts with exactly 4 moles of NH3. So this is not 1 sig fig and 1 sig fig. It's unlimited sig figs. So we don't worry about it. We just take the sig figs from our data. So we need 3 sig figs. So 3.48 moles of O2 is the answer to our problem. Okay, let's do another one. How many moles of tetraphosphorus dicoxide are produced when 1.84 moles of phosphorus are burned? Oxygen is always a reactant when something is burned. When we have burning, that means we have a combustion reaction. Okay, so we need to write our chemical equation. So how many moles of tetraphosphorus dicoxide are produced? So that means that this is our product. We can see we have a prefix system name. So our formula is P4O, deca is 10. Are produced when 1.84 moles of phosphorus, so that means phosphorus is a reactant, are burned. Oxygen is also a reactant. Remember, oxygen is a Hofbrinkel, so we must write the oxygen as O2. Now we have our formulas. We can go ahead and balance. So we have 4 phosphorus here. We need 4 phosphorus here. 10 oxygens. We need 10. So I took a little shortcut for balancing, which you can do. So now we have 4 phosphorus and 10 oxygen on each side. We're balanced. So now we're going to go back and put the information underneath the proper substance. we're looking for the moles of tetraphosphorus dicoxide, so X moles. And we're given that we have 1.84 moles of phosphorus. And we don't care about the oxygen. Now we use dimensional analysis, like always. So X moles of P4O10 equal 1.84 moles of P for phosphorus. Multiplication sign and crossbar. So moles and moles, different substances, we look at our mole ratio. So we have 1 mole of P4O10 for every 4 moles of phosphorus. So 1 mole P4O10 for every 4 moles of phosphorus. So now moles of phosphorus cancel out moles of phosphorus. The units on the right match the units on the left that I'm looking for. Put in my unit of moles of P4O10. Unlimited sig figs, 3 sig figs. So our answer needs 3 sig figs. So we do that calculation. And our answer is 0.46. That's what our calculator tells us. But I just said we need 3 sig figs, so we have to add a 0 there. Remember, when you have a decimal point, you go to the end of the number. So 1, 2, 3 sig figs. That 0 is important. All right, I think this is our last problem here. So now we have magnesium metal reacts with aqueous aluminum nitrate to produce solid aluminum and aqueous magnesium nitrate in a single replacement reaction. How many moles of magnesium are needed to produce 4.2 moles of aluminum? All right, so let's write in our substance formulas. So we have magnesium metal. So that is neutral magnesium, magnesium by itself, and it is not a Hofprinkel. So we just write Mg. It reacts with aqueous aluminum nitrate. So aluminum has a charge of 3+ in a compound. Nitrate is NO3 minus. Cross those charges, and our formula is Al parentheses NO3 parentheses 3. All right, so magnesium metal reacts with aqueous aluminum nitrate to produce, yield sign, solid aluminum. So that is aluminum in its elemental state. It's not a Hofprinkel, doesn't have a charge when it's in its elemental state, when it's by itself. Solid aluminum and aqueous magnesium nitrate. So magnesium is a 2+ ion, nitrate NO3 minus, cross our charges. So our formula is MgNO3 2. And then we need to balance that equation. So let's see, I've got 3 nitrates here. I'm going to put a 3 here. 3 times 2 is 6. I'll need a 2 here to get 6. I'll need a 2 here and a 3 here. So when you balance it, you can go ahead and list your elements in the nitrate group and balance the way I showed you. I just did a little shortcut there. Okay, so let's look at our problem. So it says how many moles of magnesium, that's our X, are needed to produce 4.2 moles of aluminum. So when I do it like this, I can easily see what I'm going to need for my mole ratio. Do the dimensional analysis. X moles of Mg, set it equal to what we have, 4.2 moles of Al, multiplication sign and crossbar. Aluminum needs to go in the denominator to cancel out. Our coefficient is 2. So we have 2 moles of aluminum for every 3 moles of magnesium. Moles of aluminum cancel. We have the unit that we want. Put in our equal sign. Moles of magnesium. Unlimited sig figs. 2 sig figs. Our answer gets 2 sig figs. So 4.2 times 3 divided by 2 equals, and we get 6.3 moles of magnesium. Now, if you were actually going to do this, and that is what you really needed, you don't have a molometer in the lab to be able to measure 6.3 moles. You have a balance, you need grams. So that's what we're going to be doing in our next lesson. We're going to do reaction stoichiometry involving grams.